Okay, so here we have two different data sets and we have fitted a line to these data sets, right? The question says which model will give more training error, right? Okay, so first of all we need to understand what is training error, right? And we also need to understand what does it mean to fit a model or fit a line to a model, right? Fit a line to the data set, right? Or fit a model to the data set. So fitting a line or fitting a line or a model. So we use the word line in case of linear regression because in linear regression we assume that we always fit a straight line, right? So what does it mean? It means that we will try to minimize the training error. Now again, what is training error? Training error is nothing but the error of each data point. So suppose the line is a plus bx, right? Then the error is nothing but a plus bx minus y. This is the sum. This is the difference between the actual data point, which is y. Y is the observed data point, which is the. So what does the data set look like? The data set is like xi yi, where both xi and yi are real numbers, right? And then we have I running from 1 to n, right? So this is the data set, right? Now we will look at the observed value of yi, take difference with the predicted value of yi. What is the predicted value of yi? A plus bxi, right? And then we will square it and then we will sum it over all the data points, right? This is the training error, right? So we start with, so how linear regression works is that we start with this, then we take derivative with respect to a and b, and then we try to figure out using the first order and the second order condition of the derivative test that what would be the value of a and b for which this is minimized, right? So we want to minimize what? Summation of the error square, right? That is what we want to minimize. So let me call this term, say, SSE, right? Sum of squared errors, right? That is what it means. So this is what happens in the linear regression model, right? Now the question asks which model will give more training error, right? Now what we have to observe is that the difference between the predicted value and the observed value is the vertical distance between the point and the line, right? So let us say this is E1, right? And let us say this distance is E2, and so on. So for all of these points you'll have an error, right? Take the square of all those errors and sum them, right? That would be the training error, right? Similarly for the model 2 also we will have smaller errors. So observe that for in model 2 each of the lines would be smaller, right? So let me call this, say, ei prime square, and then again I running from 1 to n. So now we can observe that on average ei prime square is less than ei square, right? So we can say that ei prime square is less than ei square. So we can say that the training error of model 1, this is model 1 and this is model 2. So the model 1 will have a greater training error, right? So the answer is model 1. Okay. Alright, so here we have a linear regression model yi given xi equals w transpose xi plus epsilon, right? Where the noise follows some distribution, right? What is this distribution? This is nothing but the Laplace distribution, okay? So this distribution, so we can say that epsilon, or epsilon the error, follows Laplace with parameters mu and b. Okay, now if this is the case, right, then it is also given that mu is equal to 0, right? So we can write 0 comma b, right? Now we will use the property of Laplace that if x is Laplace with parameters mu and b, then if x is Laplace, then ax plus c will again be Laplace. A and c are scalars, okay, they are not random variables. This will be Laplace with a mu plus c as the first parameter and mod a times b as the second parameter, right? So let me call this, say, a result 1, right, r1. So using r1, what can we say about the distribution of y, right? So yi, which is nothing but w transpose xi plus epsilon, right? This will follow again a Laplace distribution with mean w transpose xi, right, and b, right, because here a is 1, right? So notice that a is 1 and c is w transpose xi, right? So if this is the case, then what is the PDF of y or yi? What is the PDF of yi? The PDF would be, so let me write the PDF of yi. So we are ignoring the constant term, so we'll say it's proportional to e to the power of minus mod. Now here we'll write yi minus w transpose xi divided by b, right? Now this is the PDF of yi, right? Now we need to find out the likelihood of the parameter w, given that we have all sample values of x and all sample values of y, right? So what is this be? This will be proportional to, so we are ignoring the constant term, so we'll say proportional to, right? Or we can write equal to some constant times, you know, the expectation term. That is also possible, okay? Now we'll say this is proportional to the product of the individual PDFs, right? So this is the product of individual PDFs of yi. Now why is this the case? This is the case because yi's are independent, right? Now why are yi's independent? Because we are assuming a random sample, right? Okay. Now this is proportional to product of, again, I running from 1 to n, e to the power minus yi minus w transpose xi by b, right? This is not, so we can write this as e to the power minus summation of yi minus w transpose xi divided by b, and the sum I running from 1 to n, right? If this is the log, then this is the likelihood, then the log likelihood would be equal to or proportional to summation of, in fact the log likelihood will have some constant, say log k, which is a constant, k is a constant, plus log of e to the power something. That means e to the power, that means only the power term, right? So we will have summation I running from 1 to n minus of yi minus w transpose xi divided by p, right? So this is the log likelihood of w. So now it asks whether the ML estimator assuming the above distribution noise is same as the linear regression with the absolute error or the squared error, right? Now if you go to the previous log likelihood that we obtained, that is nothing but log L equals to some log of some constant plus sum over of negative of yi minus w transpose xi by b and the sum I running from 1 to n, right? Now what does an ML estimator mean, right? This is actually the maximum likelihood estimator. So what do we do in a maximum likelihood estimator? We try to maximize the likelihood. So we can write maximize of L of W where x and y are given, right? Now we know that maximizing this is same as maximizing the log of L, right? But what does maximization of log L mean? So we are obviously, what are we changing? We are changing the parameter W, right? So maximize with respect to W, right? Now if we have this, then this is same as saying that we want to maximize with respect to W the summation of negative of yi minus w transpose xi by b, right? We can ignore the constant term because it does not involve w, right? Now this is same as what? This is same as minimizing I running from 1 to n mod of yi minus w transpose xi by b, because we are getting rid of the negative sign here, right? That's why we are changing the maximum to minimum. Now since again b is immaterial here, b does not depend on w, right? So we can say minimize with respect to w the sum of yi minus w transpose xi, right? Now this is same as saying that if we take in the OLS method or in the ordinary least squares method, if I take the error of I to be yi minus the predicted value of y, which is yi hat. So this is the observed value, this is the predicted value, right? And then I take the mod, right, the modulus distance. So that would be equal to what? That will be equal to yi minus the predicted value is using a line, which means I can write this as w transpose xi, right? Now again, and then what we do? We try to minimize the errors, right? So either we can minimize the errors, so mod of errors, right? Or we can minimize the square of errors, right? Now if we minimize this, right, then we will have the same problem, minimize over w summation of I running from 1 to n yi minus w transpose xi, right? So these two objective functions are the same, which means that the ML estimator assuming the noise following the above distribution, which is Laplace, right? So Laplace distribution is same as linear regression with absolute error, okay? Because in both cases we are minimizing the same objective function, okay? That is the reason. Alright, so here we have one feature and one label, right? So this means there is one x, just an x1 or an x, and there is one y, right? And we are asked to fit a linear regression model y equal to wxi using squared error, right? Okay, so to fit it using squared error, right, so we have only exactly one parameter, which is w, right, which we have to determine, right? So what we have to do, we have to again minimize the sum of error squared, right? What is the error? The error would be yi minus w into xi squared, right? I running from 1 to n. This is what we want to minimize. So to minimize this, what do? We first, let me call this SSE, right? Sum of squared errors, right? Now to minimize something, what is the first order condition? The first order condition says that the derivative of what we want to minimize with respect to w should be equal to 0, because we want to minimize with respect to w, right? So this partial derivative should be equal to 0, right? What does that mean? That means that now if you take derivative of SSE, that would imply that 2 times of summation yi minus wxi is equal to 0. 2 times summation yi minus wxi, and then we will also have a xi. Now this is equal to 0, right? What does that mean? That means that we can rearrange it to obtain wi equals, or w equals, sorry, w equals summation of xi yi divided by summation of xi square. This is what we get, right? This is how we can obtain the value of w, right? Now we also need to check via the second order condition. We need to check if the double derivative is positive, right? So we need to check if the double derivative with respect to w square of SSE, this is positive. So what will the double derivative be? Now if I take derivative once, we get that, so this is equal to 2 times summation of yi minus wxi times xi, right? Now if I take derivative twice, I would obtain two times of summation of xi, right? Times xi, right? So this is nothing but 2 times of summation xi square. Now all of them are positive, so this is sum of squared terms, so this will be positive, right? So we can ensure that this will be a minimization, right? So this w, let me call this w star, right? W star will minimize SSE. So from the first order condition and second order condition, we can say that w star will minimize SSE, right? Okay, now let's compute w star, right? So we are given the values of xi, we are given the corresponding value of yi to be 2, 0, minus 3, 1, 2.2, minus 0.1, minus 2.5, and 1. So what will xi yi be? This will be 4.4, right? 0, 7.5, and 1. And what will be xi square? 4, 0, 9, and 1. And w star, we know it's nothing but the sum of xi yi divided by the sum of xi square, right? So sum of xi yi would be 0.9 and then 12.9, right? So that would be summation xi yi, and the summation of xi square would be 14, right? So w star is nothing but 12.9 divided by 14, which is equal to 0.921, right? So the regression model is y equals to 0.921 x1, right? Now one thing to be observed is that we are assuming that this model does not have an intercept or a c-intercept, okay? Let us simply compute what does x bar look like. So x bar is nothing but the summation of xi by 4, which is equal to 0. And what is y bar? Y bar would be 2 plus negative of 0.1 plus negative of 2.5 plus 1, which is 0.4 divided by 4. Y bar is not 0, right? So typically this wouldn't be it is not a good assumption to assume that the intercept is 0, but here in the question we are asked to do that exactly. Okay. Now we are also asked to find out what would be the prediction for x1 equals to 4, right? Now that is straightforward. So in that case we would say y is equal to 0.921 times 4, right? Which is nothing but 3.684. We are also asked to find out the root mean squared error for the training data set, right? So what we need to do is we need to compute the difference between the predicted value and the observed value, square it, sum it, take 1 by n, and then take an under root. So that is the process, right? So now so the values of the observed values are given by this, right? Now we need the predicted values as well, which is nothing but w times xi. This is the yi hat is given by w times xi, where w, or we can write w star, right? W star was obtained by 0.921, right? So the first one would be 0.921 multiplied by 2, which is 1.842. The second one would be 0. In the third one we would have 0.921 multiplied by negative of 3, which is negative of 2.763. And then we would have 0.921 multiplied by 1, right? Now what we need to do, we need to compute the difference between yi and yi hat, right? So so we need to compute the difference. So that would be nothing but 2 minus 1.842, which is 0.158. In the second case it would be 0. Then we would have 3 minus 2.763, which is 0.237, and then 1 minus 0.921, which is 0.079. Now again we need to take the square of the distance, right? The square of the distance, so we need to take 0.158 square and so on. So these are the squares of the differences, and the sum would be 0.14, right? In that case we can write that the root mean squared error would be 1 by n times, or you can say 1 by 4 times, because there are 4 data points, 1 by 4 times 0.14 to the power 1 by 2. So which is same as 0.035 to the power 1 by 2, 0.035, this would be equal to 0.187. This is the answer to the question.